Hello, Math 137 friends. Welcome to section 8.3, an introduction to parabolas. Parabolas are just the graph of quadratic functions. So that being said, all quadratic functions have the same basic shape, and that same basic shape is called a parabola. Right? A parabola is sort of like a bowl shape. Either opens up or maybe it's upside down. Notice this one's a little bit wider than that guy. And this one opens up, but it's a lot thinner than that. So parabolas can be tall and thin, they can be wide and open, they can be right side up or upside down. So how has this shape come about? Well, we can see pretty quickly if we just graph the most basic quadratic function, f of x equals x squared. Sometimes students like to rewrite the functions in their equivalent equation notation. That is, just replace the f of x with y, and we can graph y equals x squared. If you're never sure what the graph of a function looks like, you can always put it in its equation form and then substitute values in for x to get the corresponding values of y. So let's see. What are we allowed to square? What's the domain of this function? Well, the domain of this function is going to be all real numbers because there's no number that we can't square. So let's start. I always like to start at the origin. I always start at x equals 0 right in the center. 0 squared is 0. Then I'm going to move to the right a little bit. 1, well, 1 squared is 1. 2, 2 squared is 4. 3, 3 squared is 9. Now I notice my graph only goes up 10, 11, 12 to 12. So I'm not even going to put 4 in because 4 squared is going to be 16, and that's going to be off my viewing rectangle right here. So now I'm going to start picking some numbers to the left of the y-axis. If x is -1, well, be careful, -1 squared means -1 times -1, which is also +1. So 1 and -1 have the same output, and that's okay. Functions' outputs can repeat. The inputs just can't repeat. So -2 times -2 is 4. -3 times -3 is 9. I'm not going to do -4 because that's going to bring me way up here, and I don't want to plot that one. It's off of my grid paper. So at 0, we're at 0. 1, we're at 1. 2, we're at 4. 3, we're already up here at 9. Right, so the right side looks like this, and it's growing really quickly. It starts to get steeper quicker. That's how power functions tend to behave. Now notice the outputs on to the left of the y-axis repeat the outputs to the right of the y-axis. So at -1, we're back up at 1. At -2, we're also at 4. At -3, we're also at 9. So this graph has the same shape to the left of the y-axis as it does to the right of the y-axis. What we have here is what we call symmetry. A graph has symmetry whenever you can fold it on a line and it's the same on both sides of that line. So notice if I fold this on the y-axis, I'm just going to get a mirror image of itself. Right? So we say that this is symmetric with respect to the y-axis. All quadratic functions display symmetry. All three of these we can fold on that middle line, which just happens in these examples to be the y-axis. It's going to be the same to the right and the left. Now, not all quadratic functions fall right on the origin as these pictures do. We can move it right, left, up, down, flip it over. And those are the things that we want to see or try to identify that happens based on the equation that we're given. So again, this is the most basic quadratic function. And this is our most basic parabola. Not all quadratic functions behave that nicely. Some are moved left, right, up or down. Some are flipped over. So given a quadratic function, we want to be able to identify all the important features in a parabola. So I'm just going to first... I'm going to just darken this guy out right here. So all parabolas have exactly one vertex. The vertex, if it's a right side up parabola, the vertex is that point right there at the very bottom of the hill. If it's an upside down parabola, it would be that point at the top of the hill. So that point, regardless if we're right side up or upside down, is called the vertex. And all parabolas have exactly one vertex. So we typically find the vertex first. Now, if I look at this vertical line right through the vertex, and imagine this vertical line right here that goes through the vertex, and I fold it on that vertical line, we're going to see that symmetry again. So we tend to identify this line right through the vertex because it is an important feature. It's not part of the graph, but it is a tool that we use when we're graphing our quadratic functions. And this vertical line that passes through the vertex is called the axis of symmetry. It's called the axis of symmetry. So all quadratic functions have a vertex. All quadratic functions have an axis of symmetry that we can identify. Also, all quadratic functions, here's my y-axis, all quadratic functions cross the y-axis. And that's called the y-intercept. All quadratic functions have exactly one y-intercept. Now, some other important features are if the graph crosses the x-axis, we call these points the x-intercepts. Okay, a graph may or may not, the graph of a parabola may or may not cross the x-axis, and we'll talk about that in a little bit later. And then the direction in which these arrows point, if it's a right side up parabola, they point up. If it's an upside down parabola, they point down. We call that the end behavior of the function. So that means eventually it's just going to keep going up forever. So we call this the end behavior. These arrows indicate or give us a direction how this eventually behaves. All right, so let's talk a little bit about those x-intercepts, because right here I state that parabolas all have exactly one vertex, they all have a y-intercept, and they all have an equation of an axis of symmetry. We may or may not have x-intercepts. How can that happen? Well, if the vertex falls below the x-axis, like in our previous example, previous picture, and it opens up, it's going to have two x-intercepts. Can you see that? I'm not sure. Let me draw it just in case it's a little light. So here's my parabola. Right. And here are my axes. Right, so if it's the vertex falls below the x-axis and opens up, it's going to cross the x-axis twice, and it's going to have two x-intercepts. If my quadratic function's vertex is above the x-axis and it opens down, it's going to cross twice. So two x-intercepts. The graph crosses the x-axis twice in this type of scenario. We could just have one x-intercept, and the word intercept is used a little strangely here because often we think of something intercepting when it crosses. That's not technically the definition of an intercept. An x-intercept is where the graph either meets or crosses the x-axis. If the graph just sits on the x-axis, that is, its vertex is on the x-axis, then we say it only has one x-intercept, and the vertex also happens to be the x-intercept. So here we'll have one x-intercept when the vertex is on the x-axis. And how we could have no x-intercepts is that if the vertex falls above the x-axis and the parabola opens up, right here, here's my vertex, it's above the x-axis and it opens up, so it's never going to cross. Or we could have a situation where my vertex is below the x-axis and it opens down, right here. So here, these never cross the x-axis. And we'll see how we can determine this by looking at the equation momentarily. Just trying to get the general feel of things right now. Whoops, sorry. All right, parabolas either open up or down. That's clear, we can see what that means, obviously. If it opens up, we call it a positive parabola. So we call this a positive parabola. If it opens down, we call it a negative parabola. And looking at the equation, f of x equals ax squared plus bx plus c. And it's just a formality that a can't be 0, because if a is 0, we no longer have a quadratic equation. And we have a linear equation. We're focusing on quadratic equations right now. If the parabola opens up or down, all depends on this leading coefficient, the number touching x squared. If a is positive, it's going to open up. If a is negative, the parabola is going to be upside down. So here, 3 is greater than 0, so it opens up. And there's the graph of that one. Here, -2 is my leading coefficient, and -2 is less than 0, so it must open down. So before we even graph it, we know that this one's going to open up and that one's going to open down just based on that leading coefficient. All right, let's next try to find, how can we find the vertex? Well, the vertex of a quadratic equation, given ax squared plus bx plus c, the vertex is an ordered pair, because it's an x value and a y value, and the x value is found by taking the opposite of b and dividing it by 2a. Now, just a reminder, where did it go? The quadratic formula says x is equal to -b plus or minus the square root of b squared minus 4ac, all from our last section, all over 2a. The x coordinate of the vertex is just the quadratic function template without the radical part. It's just -b over 2a. Once we find -b over 2a, to find the y value, we take this number and stick it back into the function. So y is equal to the function evaluated at -b over 2a. And this looks a lot worse than what it is. This is just telling you, plug the value you got for x right here back into the function to find the y value. So we find the value of x, looking at my quadratic equation, we find the value of x by taking the opposite of b and dividing it by 2a. That's going to give me the x coordinate of the vertex. And then to find the y value, we just take whatever we found for x and stick it back in and use that y value. We'll do that in a moment. Once we have the vertex, we automatically have the equation of the axis of symmetry. The equation of the axis of symmetry is just x equals -b over 2a. Now you have to be really careful because that's different than this x equals -b over 2a. Here we're looking for a numerical value that's going to be the x coordinate of the vertex. The equation of the axis of symmetry is the vertical line, x equals the number, which just happens to be the x coordinate of the vertex. You need all three parts when you plop this into Alex. You need these. And you'll see what I mean in a moment. And then this number is just, this whole number is just the x coordinate of the vertex. All right, so that being said, let's take a look at this quadratic function and determine the vertex and the equation for the axis of symmetry. So the vertex is, ready? The vertex is the x coordinate of the vertex. X is going to be the opposite of b. So here, let's do this right here. This is b, and that's a. A is 1. So it's going to be the opposite of -6. I'll put the opposite of -6 all over 2 times 1. -b all over 2a, which is 6 over 2, which is 3. That's the x coordinate of the vertex. The y coordinate of the vertex, we just take 3 and we stick it into the function. So put 3 here, 3 squared minus 6 times 3 plus 5, and we get 9 minus 18, which is -9, plus 5, which is -4. So therefore, the coordinates of the vertex are 3, -4. The vertex is an ordered pair, has an x coordinate and a y coordinate. And if we look at the graph right here, this is the graph of y equals x squared minus 6x plus 5. And the coordinates of the vertex right here are 1, 2, 3, 1, 2, 3, 4, -4, 3, -4. Now the equation of the axis of symmetry, I'm going to abbreviate it AOS for axis of symmetry. The axis of symmetry is an equation, and it's so simple. You just have to remember to do it. The axis of symmetry is the vertical line that passes through the vertex. And the equation of this vertical line is x equals the x coordinate of the vertex. So it's x equals 3. You need to write, when Alex asks you for the equation of the axis of symmetry, you have to write x equals 3. So you have to write the x and you have to write equals. If you just put 3 in there, it's going to mark it wrong because the equation of the axis of symmetry is an equation. So you need an equal sign and you need to know that it's a vertical line, and that vertical line, all vertical lines are x equals some number. All right, so that's as simple as that to find the vertex and the equation of the axis of symmetry. We always want to find the domain and the range of functions. The domain of all quadratic functions, remember the domain is the set of inputs, the set of allowable inputs, and the domain is all real numbers. Interval notation would be the whole number line, which is -infinity to +infinity. Now, sometimes when we do application problems, we restrict the domain. Maybe our application problem has to do with the height of a ball after a certain time, and we can't talk about the height of the ball before we throw it. So in that case, we'd have to restrict the domain. But don't worry about restricting the domain unless it clearly says so in the problem. The range is your set of outputs. What do all the y values look like? Now, the range is not as easy to define as the domain. The range is not all real numbers. This doesn't go from -infinity to infinity. The range depends on the y coordinate of the vertex. What do I mean by that? So it depends on the y coordinate of the vertex. So remember, your range is how the y values behave. So if we have a right side up parabola, all my y values are going to be from this height up. So the lowest y value is going to be the y coordinate of the vertex, and then it's going to go up to infinity. So if we have a right side up parabola, the range is always going to be, we use a square bracket because it includes that y value. So this is the point xy. And then it goes on forever, and we always put a parenthesis after infinity. If we have an upside down parabola, this is the highest it goes. The y values never exceed this y value, and it's all y values below that number. So if xy is the coordinates of the vertex, and we have an upside down parabola, the range is going to go from -infinity. -infinity is always on the left side of the interval. And it's going to stop as high as y. It's going to stop at y. That's just how high it's going to go. So this y in the range is always the y coordinate of the vertex. Right there. So the domain is always all real numbers unless otherwise stated, and the range is the y coordinate of the vertex. All quadratic functions have either a maximum or a minimum value. The value is how high or how low it goes. So once you know the range, you know the maximum or the minimum value. It's always the output, the maximum or minimum value. Anytime you see the word value, this is screaming y. Y, the y coordinate. So it's always the y coordinate of the vertex for quadratic functions. So the maximum value would be right here, how high it goes. So you would have a maximum value in this scenario, how high it goes, high point. And you would have a minimum value for a right side up parabola, right? And it's how low it goes, or the lowest point. None of this is complicated, it's just tricky because there's lots of little details to remember, and tricky is often harder than hard. All right, let's talk a little bit about the intercepts. The y-intercept is super easy to find. All quadratic functions have exactly one y-intercept. To find the y-intercept, set x is equal to 0 and solve for y. To find the x-intercepts, well, we could have either 2, 1, or no x-intercepts. So to find the x-intercepts, you set y equal to 0 and solve for x. Right, and this is where it gets complicated. We have to refer back to our everything we learned in chapter 6 and chapter 8 when it comes to solving quadratic equations. So to find the x-intercept, you're setting the quadratic equation equal to 0 and you're solving for x. Whoops, this is a typo. We're going to ignore this and I'm going to fix that. If the discriminant is positive, you will have 2 x-intercepts. If the discriminant equals 0, you will have 1 x-intercept. That's when you have a perfect square trinomial and the vertex sits on the axis, so 1 x-intercept. If b squared minus 4ac is negative, then the quadratic function, the quadratic equation, will have 2 imaginary solutions, and we don't see imaginary solutions on graphs. You will have no x-intercepts. So the x-intercepts are just the real solutions to the quadratic equation. So x-intercepts are the real solutions to ax squared plus bx plus c equals 0. Now remember, imaginary solutions come in conjugate pairs. So if this has an imaginary solution, it has 2 imaginary solutions, thus no real solution. So if your quadratic equation has imaginary solutions, it does not cross the x-axis. The whole parabola either floats completely above or completely below the x-axis. If your discriminant is either 0 or positive, you're going to have either 1 or 2 x-intercepts. All right, let's see if we can put this all together and do a couple of examples here. So graph f of x equals 2x squared minus 8x plus 5, and identifying all the important features. So in your homework, you're not typically asked everything at once, but we are going to do everything. So does this open up or down? Well, we look at the leading coefficient. The leading coefficient is 2, so we know it's going to open up. So we always keep that in mind as we're graphing, that we make sure we get opens up. A, the leading coefficient is 2, which is positive. The next thing I tend to identify is the vertex. Right? The x-coordinate of the vertex is going to be the opposite of b all over 2a. And it's 8 over 4, which is 2. So that's the x-coordinate of the vertex. The y-coordinate of the vertex, well, we just stick 2 back into the function. So when we stick 2 into the function, we get 2 times 2 squared minus 8 times 2 plus 5. And then we carefully do the math here. 4, that's 2 times 2 is 4. 8 minus 16, negative 8 plus 5 is negative 3. So therefore, my vertex, remember the vertex is an ordered pair. The vertex is going to be the ordered pair 2, negative 3. So I'm going to go over 2 and I'm going to go down 3. -3 right here. That's my vertex. So keep in mind, the vertex is always an ordered pair. So you're looking for an x coordinate and a y coordinate. Once we know the vertex, we know the equation of the axis of symmetry. The equation of the axis of symmetry is x equals the x coordinate of the vertex. X equals 2. Now it's not part of the graph, so I'm just going to do it lightly in this yellowy green color, but this is going to help me draw my graph. So we have to remember it's going to be the same on the right and the left side of the equation of the axis of symmetry. So equation, make sure you include the x, make sure you include the equals and the value of 2. All right, so next I think I'm going to find the y-intercept. I think that's the next easiest thing to find. To find the y-intercept, we just stick 0 into the function. So f of 0 is just going to be 2 times 0 squared minus 8 times 0 plus 5, which equals 5. Right, so it's going to be at the point 0, 5. So when x is 0, y is 5. So it's going to cross right there. There's my y-intercept. Now, the y-intercept, this one gets a little tricky the way they ask you. They may say the y-intercept, give your answer as an ordered pair. So they're looking for x equals 0 and y equals 5 as an ordered pair. Or they might say y-intercept and give you y equals, and you would just say y equals 5. So just be careful. Look how Alex is asking for your notation. Now, one thing that's really cool about using my axis of symmetry, I know that this guy has a partner point exactly in the same spot on the other side of the axis of symmetry. So I automatically know that if I was to fold this right here on this line right here, I would know that there's a point right here that's the same height as this point and the same distance from the center. So I automatically, without even using my equation, I know there's a point over here it's this guy's buddy point. So it's going to be the same height as 5, because when I fold it on this line, it wants to overlap. And notice this is, here's 1, right? Here's 3. So this is 1, 2 steps away, 0 to 1, 1 to 2, 2 steps away from the axis of symmetry. So the point 2 steps away to the right is going to be this guy's buddy point. So automatically I know that the point 4, 5 is another point on this graph without using this at all, because I know it has to have a matching point. So now Alex is going to say plot. I think if I ask you to plot 5 points. So the next logical thing might be to find, we know this is going to cross the x-axis because here's my vertex and it opens up. So it has to cross the x-axis. So let's find my x-intercepts. Right, so my x-intercepts, well, we have 2x squared minus 8x plus 5 equals 0. And you can do this however you want. If it's factorable, you can factor it. I'll give you a hint right now that this does not factor. So I'm going to get x is equal to the opposite of b, which is positive 8, plus or minus the square root of, I'm going to put 64 right underneath because it's b squared, minus 4 times a times c, all over 2 times a. Now our x-intercepts are the solutions to this quadratic equation. And hopefully you've seen by now that solutions to quadratic equations aren't always nice whole numbers. So you can't expect this to come out to be a nice, pleasant whole number. All right, when I do this, I pop this in my calculator. I'm going to get x is equal to 8 plus or minus 64 minus 40, which is 24. So it's going to be the square root of 24 all over 4. Now we know the square root of 24 is, well, we simplify the square root of 24. Well, 24 is 4 times 6, so it's 2 square root of 6 all over 4. You might say, how do I identify those as my x-intercepts? Well, I'm going to split this up into its 2 pieces. It's going to be 8 over 4 plus or minus 2 square root of 6 over 4. And I'm going to clean that up, and that is 2 plus or minus the square root of 6 all over 2. So therefore, my x-intercepts are x is equal to 2 minus the square root of 6 over 2 and 2 plus the square root of 6 over 2. Remember how I said the x-coordinate of the vertex is just the part of the quadratic equation without the radical? 8 over 2 times 2, which is how we got the 2 here, 8 over 2 times 2. And so it's not a coincidence that my first x-intercept is a little bit to the left of where the axis of symmetry crosses the x-axis, and the other one's a little bit to the right. So how do we plot these? Well, now here's where you pull out your calculator. You got to be really careful with the math here. I'm just going to get an idea of about what this number equals so I know where to plot it. It's going to be 2 minus second square root of 6. Make sure you close that parenthesis because I don't want the divided by 2 in there. So this is about 0.8. We only need one place after the decimal for graphing. 2 plus second square root of 6. This time I'm going to add, divide by 2. Whoops, I did already add, divide by 2. I'm trying to do 2 things at once. And that's about 3.2. Right, so now because this is symmetric, it should cross the x-axis about the same distance from where the axis of symmetry crosses. So 0.8 is about right here, right before 1. And 3.2 is right after 3. So we can see that it's a little more than 1 unit. So there are my 5 points. And I'm going to draw, you can, if you want, draw a couple more, like graph a couple more points. Like I'm going to do, what if x is 1? Just because if Alex asks for 5 points, I'm not going to be able to put these in. So if x is 1, I'm going to go up here. I'm going to go 2 times 1 squared, it's just 2, minus 8, which would be negative 6, plus 5 is negative 1. So I know this goes to the point 1, negative 1, right there. Right, so that would be another good point to draw. Now we also know that this point has its symmetric buddy right over here. So at 3, it's also negative 1. So that would be enough points to draw my parabola. And once you have your 5 points and you hit draw, it will put the parabola nice. Now remember, all quadratic functions have this nice parabola shape. So if you put graph and it gets all wonky, then you know you did something wrong. All right, so what's a couple other important features we can identify here? How about, let's talk about what is the domain? Well, you would tell me the domain is all real numbers in an interval notation that's negative infinity to infinity, because the domain of all quadratic functions is all real numbers. Now the range. Now remember, the range depends on the y coordinate of the vertex, and the vertex is 2, negative 3. All my y values are from negative 3 up. So my lowest y value is negative 3, and then my y values shoot off to infinity. So my range would be negative 3 to infinity. And then it might ask you, do you have a maximum value or a minimum value? Well, anytime we have a right side up parabola, we're going to have a minimum value. And the value is how low it goes. And it goes all the way down to negative 3. That's the lowest value or output of the parabola. So it's negative 3. If it asks where it occurs, that's when you tell the x value at 2. So the lowest value is negative 3 and it occurs when x is 2. So this is everything you need to know about that quadratic function. All right. Right, they don't